In this talk is to introduce this semantic web, the vision of semantic web at a very high level. I'm going to take a lot of liberty and make things simple for the clarity. I think during the discussions we have, we need to go into more details and interact on these things. So, I just start out with a few quotes here. In the White House paper on MGI, there is a discussion about data exchange system that will allow researchers to index, search, compare data for greater integration and collaboration. And in discovery stage, it is crucial that researchers have access to the largest possible data set upon to base their models and so on. So the point here is that this is a broader vision, and the proposition is that the semantic web technology and the standards are indeed the technological tool to achieve what is outlined here. A similar or related quote here, integrating materials, computational tools, and information resources, computational and analytic tools already in use in engineering fields, so that promise to shorten the cycle. And here is a quote from Chakwad. Our community is entering a new era where individual computational tools and dispersal and modeling data must be brought together to create integrated tool sets made available to materials manufacturing, design engineering. And so these are the these are the requirements, these are the goals and objectives that I would like to show how semantic web technologies can help us reach. So the fundamental true interoperability and integration of the data, and to make the data that is generated throughout the life cycle. When you are designing materials and you're collecting the data, when you have a process for creating the materials and the data is created throughout the steps of the process, and then when you are analyzing that for giving the data to your tools to see whether they perform or you find the characteristics that you're looking for. All these things generate, this whole life cycle generates a lot of data. I'll draw an analogy. A while ago, about a decade ago, I worked with a biological scientist. They did the mass spectroscopy. So you put some biological element and the cells, and it goes to multi-step process, and single run of that will create 5 gigabyte of data. It may not sound too large now. There are many processes that can create larger data elements than that. But think about a biological scientist facing with 5 gigabyte per run, and there are many runs that you will have. The point here is that the technology that I'm talking about would allow you to understand each element of the data generated throughout the process and query it at the end. Right? So instead of when we got started with that project, all the data went into tens of or hundreds of files. The files were created, stored on different databases or file systems and document systems. And at the end, the guy is facing so much of the data spread over multiple computers, and then he has a lab note that has this file name has this data kind of stuff, right? And from there on, for him to be able to analyze all data is a very difficult challenge, right? So how do we bridge all that stuff, right? And the technology that we have now bridges that. Fundamental to that is to go away from the low level. Here you see the data and the syntax, like what is the file name and what is the structure, whether it is in XML or whether it is a comma limited format, CSV format, or whether it's in relational database, to something that is meaningful. What does it mean to the discipline? Right? What does it mean to the science? What does it mean to the engineering? So that the human who has the need to access and analyze the data can ask the questions from an application perspective, from the use perspective, rather than deal with the files and the formats and all those low-level stuff. Right? That is the fundamental thing you have to do. You can see the examples here where you is talking about audio bit rate all the way to say, oh, there is abscess in the upper abdomen. That going from that low-level information to that high-level thing that matters to human decision making is what we need to do. That is what the semantics is about, from syntax to semantics. Right? So fundamentally, the technology is about obviating the need to deal with the syntax and providing the tools to deal with the semantics. So the term semantic web was coined, although in the principle this thing was used long time ago. I was at Belcore when we had a commercial tool we called semantic information brokering, where the data was on the web and browsers. We had browsers that allowed you to search the data. But Tim Berners-Lee, the father of the web, coined the term in 1999. He had a book, Viewing the Web, a very nice book, talks about the history of the web. Then there was an article in May 2001 that became very popular. Although that put out, in my opinion, a rather AI-centric view, talks about agents and things of that nature. It so happens that in that particular form, semantic web has not particularly been realized much. But there is a practical form of semantic web that has been realized very broadly, and that's what I would particularly talk about. So I had started a company in 1999. It was called Tali. Tali means applause, and it was bringing together of digital broadband and internet and internet and TV and things of that nature. And then we developed a bunch of tools. So, for example, this was a patent that was filed in 2000 and awarded in 2001. You can see the title that talked about browsing, searching, profiling, personalization, advertisement, all that using semantic technologies. So the idea was, you can see on the right-hand side, some sort of taxonomy, right, of the variety of things. You have sports and variety of sports all there, right? So you develop these kind of models, and behind the models you have a knowledge base. You have actual facts of all the stuff. For example, in the baseball, you will say for this team, this is the member roster, or this is the player roster. All that detail will be there in that. So that is, it comes in various forms. It comes in the form of taxonomy all the way to more formal form called ontology. And this is, for example, the application that my company developed. This one does audio-video search on the web, search for audio-video content on the web. That particular application by itself may not be very important here, but the point here is that here you ask Madonna as in artist versus Madonna as in a singer, right? So Madonna as an artist may be Avita, will give you the movie Avita, and the system understands the context of the use of the term, versus Madonna as in a singer, and you get the albums and things of that nature and all the tracks. So that is the semantics, right? Because the text Madonna may have multiple interpretation, multiple roles, multiple Madonnas may be there. But making the sense of it is the semantics, and the system brings that, and understand that. So here there is a directory aspects where you type in commerce one. These companies know more here, but I'm deliberately showing you old slides. It shows all the competitors of that particular company, and it shows you all the partners, and it shows you all the technologies that use it, and so on and so forth. So let me make a very simple but hopefully effective introduction to the semantic web. There are three things, three main things to understand about semantic web. Number one is what we call ontology and associated knowledge, and it comes in different forms. So you may hear the words taxonomy, nomenclature, domain model, ontology. All these terms are there, and we can discuss the nuances a little bit later on if necessary. But the point here is that there is some form of agreement among the experts and the user base that is captured. And there is some forms of facts about that particular scope of the model that is also captured. Right? this material performs in this to that range. This is a fact. Right? You capture that if it's already agreed upon by the community as an example. Once it is captured in a machine processor form, the tools, the software understand that. So the humans does not have to worry about all that when you search. The system understands that, right? So, and there are languages, formal languages and standards to capture all that. So that is number one. Number two, I went to the. And number two is called annotation. So here, basically, it is about labeling the data. You want to, you have a text, you have some data, you have text of any form, you have tabular form, you have figures, you have textual data, you have relational database, and you basically say something in here means what is described here in my ontology, in my domain model. So it gives you universal meaning to whatever the data there is. Right? So that is called semantic annotation, or there are techniques to automatically do that for you. So remember the example of the mass spectroscopy data that I talked about? Well, there is a model of mass spectroscopy related discipline and the biological discipline. As the data is created automatically, all the data gets tagged. So the data gets meaning associated with that, so the subsequent tools understand what that means. So it can be done manually, semi-automatically, automatically. And the third is reasoning and computation and all variety of use of that data, all the variety of use of the semantic data. So you have semantics enabled search, integration, answering of complex queries, finding the path, defining hypothesis, and you have inferencing and reasoning techniques and so on and so forth. Right? So there's a whole variety of all that stuff. Let's look at ontologies. So there are very simple ontologies. Here I show a subset of a drug ontology, pharmaceutical drug ontology. And so you have a prescription drug, and you have brand name, and you have a generic name, and all these things are defined. To very complex ontology. This is kind of things you might need in material science in some cases. Here I have a biological process. We can argue whether material science is more complex than the human body. Right? We can discuss that. But both of them can be very complex. So here, for example, a particular, in the presence of particular enzyme, particular biological process takes place. So this is that biological process that takes place, chemical reaction of sorts. And we need to be able to model that. Right? So this is how the web ontology language, which is standard, in which we are formally modeling what is happening here. All I want to show you is that very complex stuff can be modeled if we want to model that. Right? Once modeled, it is something that is understood by a machine, and it is something that many people can agree upon. And then you don't have to worry about the textual interpretation of the text that you have, and so on and so forth. Now, we at Noesis have done this kind of ontology development, semantic applications in many domains. We've done a significant amount of work in biology and healthcare and clinical data and so on and so forth. Many of them are public ontologies that are used by others. There are a whole bunch of standards. Wright State University is an official member of Worldwide Web Consortium, which makes standards in this discipline. So for example, and in fact some of the work we have done have led to standards from Worldwide Web Consortium. Here I'm showing you some of the standards relevant to the semantic web, where you start with the syntactic data here, and then you get semantic web. So you start with a resource description framework and URI. URI is some way of talking about an object on the web in a universal way, in a way that you address where any object on the web is addressable, that you can talk about it. So your data is no longer limited to your database. It's there on the web. Once you have that link, you can get that. And RDF is the model, just like your relational model. You have a model called RDF. Fundamental distinction between, say, relational database and relational model and RDF is that relationship is a first-class object. That means A is connected to B. You don't only talk about A and B, but the connections also. And that is very powerful. That fundamental thing, that you're not talking about nodes, but the edges that connect the nodes, and name them, and talk about it, and reason about it. That makes the fundamental difference between the other technologies that existed before and the semantic representation technologies. Then there is a schema, just like there is a schema, and then there is a richer way for representation models. So this you represent data here, the models you represent in the web ontology language. Then there are query languages. Sparkle is a query language for RDF and so on and so forth, and many other things. Now we started with, in this projects that we have in this area, we started with the development of materials ontology. So here you can see a taxonomy part of the ontology. There is a lot more than what you can see here, but you can see a variety of things being modeled here, right? Now, currently we are modeling this, by a small group of people. Claire has a lot of knowledge and he guides us to something. We get something from ASM as a taxonomy to bootstrap this thing. Raghu and his student bring in knowledge from material science. But in principle, we can do this on a worldwide scale. For example, in the area of clinical sciences, for example, there is a code for ICD-9, ICD-10. When we go to doctor's office, they use this coding to bill for that, right? There is a next generation of that called ICD-10 that is being developed by people, the clinicians, doctors all over the world under the aegis of United Nations. And so there are many people all over the world that are using these tools, which we can also available to this community, and many of us can collaborate. So the hope is that should we be convinced that we want to do that kind of stuff in any sub-area of material science and manufacturing, we have the tools to engage a large community of engineers and experts so that we can bring all this together, because no one single person has all the knowledge, right? Here you can see more detailed stuff being modeled up about some aspect of that, control and sensor parameters in material ontology. Here you can see object properties. So you take one particular object, any particular object, and you might be defining whole variety of stuff. You can see some examples of those things. Here, these subset, some related things to materials, these biomaterials. And so we have a project in biomaterials. In this particular case, we have biomaterials ontology that is being developed. And here it shows a whole bit of detailed things that are put about each of the terms that are defined in the ontology, so that there is a lot more precision and concreteness of what we model. So let us talk a little bit about semantic metadata extraction and notation. Essentially, you give us any type of object, and we write what we call extractors that will create the metadata, right? And so the idea is you can do it manually, but that doesn't scale too well. It is very complex. You might have to do manually, and we have tools for that. Or if it is something that can be defined well, it can be all done automatically. So humans are not involved in doing that. So here is this is a slide from year 2000. In fact, 2002 in this case, August 2002, for the technology that we developed in 2001, where you can see that this is a text, but the system understands that. You see here, the standards and poor 500 index is a financial index. Financial index is a concept in the ontology, and it has a number of financial index. For example, financial index there are many indices out there, right? One of them is Standard & Poor's, another is Dow Jones index of 30 stocks. And the point here is the system understands automatically that thing, that string, is no longer a set of strings Dow Jones Industrial Average. It is actually, as a whole, an index. Right? It's not just Dow Jones, it can be a company by itself. Right? So these are the kind of things that you have. Not only that, and it understands many other things. This is a company name. It understands the relationship that these two companies compete with each other. Right? And this is all automated. Right? So imagine now you're generating a massive amount of data in material science and in manufacturing, and imagine that you have ability to tag or label or annotate all this data automatically such that you can use now concepts like, oh, give me any article about a Dow Jones news retrieval that occurred in last hour, that appeared last hour. Now this becomes much easier. You don't have to spell out all the 20 stocks, right? The system knows any one of that Dow Jones news retrieval has these 30 stocks, and it will automatically map the things and find for you. Right? This is just some exact queries that you can do. Here is some biological data, clinical data that is coming in, and it is getting tagged with concepts and the ontologies that we have, for example. So what happens is, once again, putting all together, we deal with many kinds of information. For example, we deal with textual data, we deal with structured and semi-structured data, and relational databases, and XML files. Your multimedia content, your sensor data, all these, here are your ontologies of models. All this data can be annotated, so you have metadata, all these are annotations, and then you have applications for that. So search, integration, analysis, discovery. Of course, each of them have a lot more that we can talk about. I'm just giving you very high level view. So let me give you one. A real system. This is a system that was deployed in January 2006 at a very busy practice. So what is happening here is that in this case, as somebody, this is a physician or physician assistant that is creating medical record. When you go and go to doctor's office or hospital, they have to generate electronic medical records. And here, all the medical record is automatically generated. So, sleep apnea, all the possible sleep apnea information is made available. You can choose the right one. It can be done in a reverse manner, where if you have text, I can find exactly what you are talking about. Right? So, either way, whether there's a process for you to find the most appropriate use of a term, or automatically annotating can be done by the system. Here, you are talking drugs and quantity. The system understands that there are rules. You cannot be giving nitrate and Viagra together. Otherwise, there is a serious problem with the heart rate. Right? So, system will really alert you if the doctor ever tries to do that. Right? Or if you have a particular treatment, there must be corresponding diagnosis mentioned. Otherwise, the record is not complete. Right? So, this kind of stuff that this application allows you to do. But in the process, understand that we have done all the three things we talked about. We have ontologies, like I showed you drug ontology. We have annotations, and we have reasoning, like if drug-to-drug interaction, right? Now I have another application. It's called Intelligence Analysis Need to Know. So let us look at that application. So in this case, you have set of ontologies. You have a variety of data in different formats. Data gets automatically annotated, and the application is about if there is an intelligence analysis. There's a lot of problem inside the thread, meaning people are going to the places that they don't need to go to. That's the one major problem that intelligence agencies have. So there's some regulations about it, and this was in that regards. So if an analysis has been given a task to investigate certain things, it should be possible for you to understand whether the person is fishing around the right places or going somewhere totally where not authorized. Right? From a content perspective. So this is not a simple thing to do, but I just wanted to show you what it takes to create this application. So give you kind of warm and fuzzy feeling. So this is ontology. terrorism in this case. We are focused on terrorism, a particular thing. This was in 2004, post 9/11 world. This is ontology, visualization of ontology like terror event and all those data model. Now this shows you variety of sources from which we collected data automatically to populate the ontology. So ontologies have concepts and you have knowledge, facts. So the facts in this case were all kind of terrorism events, all kind of terrorist groups and so on and so forth. But there are many different sources. This was the source of United Nations 1267 committee list. Here is a source of Bank of England census list. See, all this data is in different format, and yet here is a source of International Policy Institutes, counterterrorism. Point is that all this data can be gathered together, and you can generate this comprehensive knowledge base of facts. So this is the ontology, how it looks like, visualization of that ontology. Now what happens is, I somehow graphically generate a query. In this case, I'm going to jump around and just to give you. So this is annotation. You can see that things in blue are concepts defined in ontology. The things in green are lexical concepts that are potentially meaningful, like a good search engine would do. And things in grey are special things like date. All this is done automatically. In those days, we used to do 1 million documents per hour per server. These are some internal external represents. Query formulations graphically. And then the query is articles about terrorism in Middle East. And here you can see the system comes by with color coding, green to red. Red are not related. Greens are related. So how? This article was found to be very related because the concept of the query, terrorism in Middle East, and what is in the article were closely related. So system could tell these are all the things in the article and very close to what query has. They are closely related, hence they are relevant. I have other example where this is less related. For example, there was a group, Abu Sayyaf in Philippines, where they had Middle East ties. So this is not Middle East itself, but they have ties. And they are less related, and there is a longer chain of connection. And here is something from the LTTE, which was in Sri Lanka. These are least related because there was no known Middle East ties, although there was terrorism. And very long chain of connection. But this gives you an idea of kind of stuff that you can do. Let me end. Let me end this particular talk with just this general idea and very high-level description of the semantic web. Any questions? I think I took some more time. Sorry about that. Yes.
The semantic web, it looks like the challenge is to get all of the edges. What we do is we obsess with the vertices. We start talking about semantic data. It's that you've got the relationships between the objects. And the challenge, I suppose, is to get everything all linked up. But you can divide the world into two classes of problems. Rare problems, which is the terrorist problem. You want to find some obscure connection. And that's very relevant to behavior management military systems. The other one is to manage your individual graphs cut into very strongly interactive. So elements or subsystems that deeply interact. Then you start talking about material development. And those little subgraphs would be very important to like small companies and one products. Anybody doing any work with graphic?
So the question is about, I think this is a very perceptive observation here that data, and then you have this metadata represented as sort of graphs, and two very different forms of things are identified. In some cases, there are exceptions or very tenuous links and long chains, and there are in some cases applications that is important. In other cases, you want to be able to see things are highly connected and close by, and some little change could change some other things like that. So there are a variety of processings that this technology makes it possible. Here focusing on just the relations aspects of it. I am not aware of these applications in the material science or manufacturing per se right now. That is what we want to go about. Similar applications I can find in financial services, I can find in clinical research, pharmaceutical research, and biomedical research and translational research, and we have been involved in all of those. The whole idea here is, and the whole idea of this workshop, or part of the idea of the workshop is to say that, look, other disciplines, particularly biomedical, and my next talk will talk about that, has done quite a bit in this general area. There are many applications. I just showed you two of many applications and many ways of computations. This is done routinely. The technology is literally mature. Nothing comes for free. There is no free lunch. But putting in some effort, maybe there is a lot bigger rewards than the effort that we are putting. So, yes.
A lot of programs, like right now, when we finish, I'm a material scientist, I'm not a data person, but when we finish the program, it's in the form of generating a report and a tremendous amount of data. How much effort is it to take the report, all the data, and to place it into an electronic form that is searchable at the end of the program? Is it something that requires all participants to participate in describing the data? Like, how would you go about doing that? Because that's one of the key issues that we deal with in a lot of programs, and that when the program ends, it's like the knowledge is lost in a way, and that they're, so-and-so has these data files, and they have certain file structure, and if you wanted to go back and reinterrogate the data, good luck.
You got to call. Yeah, you got to go find that.
Excellent question, and for this there is I think very good answer, and in fact one of my next talks will give explicit demo of this kind of stuff. So the question is about, projects leave behind a lot of data, and then finding all these things huge task or difficult task, data will be lost. If you don't know how to find the data, what value that is. Let me give you an example. On the PubMed, there are more than 20 million abstracts. Every article published, every scientific literature published in biomedical and clinical area, medicine, gets catalogued by PubMed. So when authors write these kind of data and publish the article, many of them are 20 years old, 10 years old. Obviously, they are just texts. We, for example, have developed an ontology. In this particular case, there was a project for AFRL for the human performance and effectiveness directed. We created human performance and cognition ontology. So with regards to that ontology, we index the entire corpus of all the abstracts, and it is all searchable from perspective of that model. So the cost will be primarily to have the ontology or model that becomes the framework for you to search for the data when you want to search for the data. That will be the main cost. Ability to index all the data automatically is not hard. And then have the tools to search all that is also not hard. Most existing tools that are there, we have, others have, can be adapted to do that work. The fundamental challenge is that is what Claire has been promoting, is to have this materials ontology and variety of things. And again, we can't develop entire things all the time. And we'll need participation of people to model the knowledge and come to the agreement. If that is there, then the rest is thing. One possibility will be that as part of the program, you insist that they give you the model, the schema, and the rest can be done automatically, for example.
Because that's one of the real problems in material science, and that we'll take something and distill it down to a volume fraction and a grain size.
Yeah, we can-
Somebody says, well, that's actually a distribution, we'd like to do probabilistics on it. And the data's there, but we can't find the data that was used to derive that grain size.
Yes, and it can be done while the projects are conducted, or it can be done afterwards. Again, the main issue would be, do we have the access to a model or a concept by which we are going to search this info, index this info. Okay, so are you the next one or?
Well, I think, first of all, thank you